Yes. All right, so resume recording. So today we're going to continue talking about ensemble learning, and these are the notes. So I'm going to post this in the chat. And I started talking about this 2 weeks ago before spring break. Well, I updated the notes. So there's a lot of conversations in data science about bias in the models, especially when we're doing classical machine learning. And they ask what is the bias of our models, or even in large language models, they talk about biases in the models. And another thing is the variance. So the variance is just how spread is our data. So so when we're working with different classical machine learners or base models, and we want to minimize the variance and the bias, so we cannot do it for each case. We have to combine. And for example, if I want to decrease the variance, as I'm decreasing the variance, the bias is increasing. And if I want to decrease the bias, then my variance increases. So there is a sweet spot where you combine both, try to balance both phenomena. And when you have very high bias, you are just practically, if you're doing like a regression, you're just having an underfitted. For example, this set of points would correspond more to a quadratic function instead of a linear one, so I'm underfitting. And if I can go overhead, and if I want to decrease the bias, then maybe I'm overfitting, so I am increasing my variance. And so there's a sweet spot where you just balance between bias and variance. So this is basically one of the topics that you will find in classical machine learning, and especially in ensemble learning, where you combine different methods and models in order to have a good balance between bias and variance. Okay. So well, bias basically is for example, in this case, the bias, this is the bias axis. So if you have low bias, means that that everything more or less you are close to whatever there is the truth, right? But you can be way off, so that's a high bias. So for example, in large language models, when you are training on large language models, and for example, you just use Western literature, then your model, language model will be biased through Western literature. But if you use Eastern literature, then your bias will be towards the other end. And every culture has different values, different ways of uh, conceiving the universe, or the way they see things, different philosophies, etc. So the bias can show up. And if you want to construct a model which is very low in bias, then you have to consider uh, different resources, not only one source. Okay, so that's the bias and the variance. And this is the trade-off, bias variance trade-off. This is the curve that I was seeing. So if you want to decrease your bias, then you are increasing your variance and you are overfitting. And on the other way around, if you want to decrease the variance, then your bias increases and you're underfitting. So this is the sweet spot between the two. Okay, so when we do ensemble learning, we want every model sees different things. Every model, if you have a data set with different variables, every model will have different weights on different variables. So you have to have a combination of models and try to minimize your or balance your bias and variance. Okay. And there are three methods. One is the bagging or bootstrap aggregating, where you train models using different data subsets and you're combining through replacement, and then you obtain the output by averaging or voting, and this will reduce the variance using bagging. And the last session we talked about decision trees and how we can increase the precision of a decision tree, defining we handle a parameter alpha. They gave us a best estimate of higher accuracy in the models. The other method is boosting, where you have different models in sequence in order to correct the errors. And this is just like an iterative process, and there are different algorithms that can be used for this, like ADA boost, the general boost method, and the extra gradient boost method, and the light gradient boost method. Those are basically different algorithms. And you can find most of the algorithms in scikit-learn, except I think XGBoost and LightGBM. Those are independent. And the third method is the stacking, where you optimize your predictions using different multiple base models, and then you use different weights in order to have a prediction. All right. So what are good practices for applying ensemble learning? And you have to be aware that probably you have to be using diverse base learners or different models in order to have using different algorithms and trying to tune these models using the searching for the appropriate hyperparameters, and then you will produce models with higher variance, and you have different predictions. So you have a key thing is how to select your base models. So so for boosting, you have to select, for example, weak learners. A weak learner is something that is slowly learning, and at some point, when you combining the different weak learners, you get a improved result. And bagging works with high variance algorithms, and finally stacking enables a flexible model. Okay, so when you try to combine different models, for example, for classification, you can use the voting method, and you have three types of votings: the majority voting, the soft voting, and the weighted voting. The majority voting is just selecting the classification that most of the models agree on. A soft voting, you can assign different weights, not weight, but predictions, and try to combine the predictions in order to get a result. And the weighted voting, you give different weights to different models depending on which model, base model you're using. Okay, and in regression, well, you just use averaging because you are trying to predict a number. And okay, all right. So let's go in detail to the three methods. The bagging, the bagging, as I mentioned, you are using different learners, base learners, and you have a training data, and you construct different subsets of your data set, and the subsets is just like selecting a subset with replacement. So for example, your original data set only has like one blue cross and the purple plus, but when you select, you can select twice, two purple cross pluses and two diamonds, blue diamonds, and one circle. This other set is different selection, where you are repeating the circles, you are repeating the diamonds, and you don't have any plus signs. And the third data set subset is just you have a repeating glue crosses, and anything else. So you have created three samples with replacement, and every subset you give it to train your model, your base learner, and then you make a prediction. Look, so for example, the prediction from the first model is yes. The prediction from the second model is also yes, and the prediction from the third model is no. And then you combine the three results. And for example, you say, well, I have two models agreeing that it's a yes, so the result may be yes with more accuracy. So that's the bagging or bootstrap aggregating. And you can be using different models or base learners. And the goal for this method is to reduce the variance of the model. And this is, well, explains the method by creating multiple subsets. And you're training your models with the different subsets. And then you combine the predictions of all the models. You can just simply average using if you're doing a regression, or just use majority vote if you're doing a classification. And this is the different base models you can use in bagging. So decision trees, random forest, the k nearest neighbors, and the support vector machines. Okay. And this is an example how to use the bagging classifier from scikit-learn. So from the Ensemble library from scikit-learn, you import bagging classifier. And from the scikit-learn linear model, you import linear regression, logistic regression, and your base model would be logistic regression. And then you're going to use this base model in your bagging classifier. So you have the base estimator is the base model, which is a logistic regression, and the number of estimators is 10, just a parameter. And then you're going to train your bagging model with your training data, X train, Y train. You're going to fit, so you are training your model. And then once you have trained your model, then you make predictions. So you, with your bagging model that is already trained, then you try to predict based on the testing data set, and you have a prediction. And then you apply all the different metrics to see what is the precision of your prediction. Okay. And the same way as you are doing bagging classifier, you can do a bagging regressor. In the bagging classifier, you're trying to classify some labels. In the regressor, you're trying to guess a number. Okay, so that's the first method for the bagging. The next method will be the boosting. And in the boosting, again, you have different training data, and you have a model. You may have the same model. And these are weak learners. So you train your data, you train your model using your data, and then you see what is the outcome. And depending on you comparing your incorrect predictions with your correct predictions, then you send back again and give different weights for your training data. So when you train again the model, then you look for the new incorrect predictions, and then you turn them. When you compare them with the correct prediction, you send back to your training data, and then you add more weights in order that when you train your model, the number of incorrect predictions will be less compared with the correct prediction. So at this point, you have iterated 3 times the same model using different weights on their training data in order to improve your accuracy. So that's the boosting. It's just an iteration process. Okay, and the goal for this boosting method is to reduce the bias. And this is how I was explaining how you train your model sequentially, like an iteration, and then depending on the outcomes or the outputs, and comparing with the correct predictions, you're trying to give different weights in order to reduce your bias. Okay. And what type of base models you can use? You can use decision trees, like the ADA boost or the gradient boosting. You can, for linear regression, you can use the lasso regression or the elastic net uh, in order to improve the sparsity and try to reduce the overfitting. Remember that lasso, and when we were looking at regression algorithms, the lasso and the elastic net, they talked about the error. If you measure the error using the absolute values, the L1 error, or you were using the square of the difference, the L2 metric. So this is the same. And lasso regression use the L2 square, and the elastic net will be a combination of L1 and L2 metrics. Also, you can use support vector machines. And this is an example how to use the AdaBoost classifier. So from scikit-learn Ensemble library, we import the AdaBoost classifier. So we have the base model will be a logistic regression. This is our base model. And then we're going to construct our AdaBoost classifier using the base model, which is a logistic regression, and the number of estimators is 10. Then we're going to, once we have our boosting model, we train our boosting model, feeding the values from the X train, Y train. And then once we have trained our model, the boosting model, then we have to make a prediction with the testing data and the outcome. Then we can apply different metrics to see what is the performance of our model. Okay, so this is a classifier, boosting classifier, and the same thing we can do it as a boosting regressor. Okay. And the last method is the stacking, where we have our data and we have different base learners. And every base learner will make a prediction. And then we will have a meta learner. That's meaning that we're going to combine the different predictions in some way and try to have a final prediction. And this method of stacking is for improving accuracy. And since you're using different models, then you are more or less guaranteeing that you have a broad range of models in order to improve your accuracy. And the base models you can use are decision trees, support vector machines, the k-nearest neighbors, and neural networks. This is an example of a voting classifier. So we import the voting classifier from the scikit Ensemble library. And then we will use two models. Model 1 will be just a random forest classifier. And model 2 will be another boost classifier with different parameters. And then we will define the ensemble. So the voting classifier, we're going to be using the estimators random forest for model 1 and ADA for model 2. And the final model will be voting hard, meaning I'm going to take the majority vote. Okay, and then once we have our ensemble, then we train our ensemble using your training data. And once we have now our trained model ensemble, then we're going to predict based on your testing values, and whatever you have predicted, then you can apply all the different metrics to see what is the performance of your voting classifier. Okay. And the same way as you work with classifiers, you can work with regressors. Okay. And then, okay, so and then you can have a better result of accuracy. So this is basic, the differences between the three methods. The learning styles. For bagging, you're doing parallel trainings. In boosting, you're doing sequential trainings, and stacking, you're doing stage modeling. And what about the base models? Uh, diversity. So if you're doing bagging, you are encouraged to have different models. If you're doing boosting, remember you're just running to the same algorithm, so you don't have to have diverse base models. And for stacking, you can have different models. And the focus of each method for the bagging is to reduce the variance. For the boosting is reduce the bias, and for stacking is just improving your accuracy. And there's some strengths and weaknesses um, for the three models. Okay, so all right. So next, let's jump to our example. So we have a Jupyter notebook. So we select that, and I have it over here. Yes. And the first part is something we saw in our last session, and we're going to share this in the chat. The Jupyter, and then we will run this Jupyter notebook in Google Colab. So I will open it in Colab. Okay. All right. So I will run our first cell, which is basically most of the libraries, basic libraries. And I will be using scikit-learn model selection, the decision tree classifier, the different metrics, the plot tree, and from the metrics accuracy score, and I'm going to ignore some warnings. So execute. Okay. And we were using the penguins data set, so I'm going to read it. And I just need to have the data frame defined. Okay, I guess this is same. And okay, we need to clean this data frame. And we clean again. And yes, this last part. Okay, so we have a clean data frame, which is df. And I don't need to do this. I don't need to do this. We already did this. I'm going to jump all the way to the ensemble learning methods. Okay. Yes. And this was for a regression example using the cancer data set. Okay, so we're now in the ensemble learning. Okay. So we are going to start with the bagging classifier. So we are importing the bagging classifier from scikit-learn ensemble. And we're going to define the bagging classifier as backclf. So execute. And then we're going to, oh, I think I need to define what is X. And my bet is yes. Let me define what is X. Okay. Yeah, so I need to define what is X test and X train. I think I have to go all the way back to the penguins. Yes. Yeah, that's the part of the Okay, here. All right, so this is the DF, the data frame that we're going to create X and Y, and we we create the testing and and uh, and 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 training and testing. We have to use the train test split function. So we do that, and then we had about 333 rows of the penguins data set, and we have selected 80% to be the training data set, 266 rows, and we are going to leave 20% for the testing. So that's 67 rows. So now we have defined what is X train and X test and X and Y train and Y test. Then I can jump all the way to where I'm going to use X and Y. Okay. After the diabetes example, yes, here. So now um, I'm going to use X train and Y train to define the bagging classifier. And I'm going to make the predictions. And you can see here that the accuracy score between Y test and the bag classifier is 1. And the accuracy a score between the Y train and the bagging classifier predictor train is 0.99. So that's for a classifier, and for doing a regression, I need to use the X test diabetes. So I need to go back and read my diabetes data set. Okay, yes, here. So I'm going to import data sets. So I'm going to import the diabetes data set. And I have my DF sample now. And here I have my diabetes, X diabetes and Y diabetes. And then I'm going to split the diabetes into training and testing using 20% for testing. And then I can go all the way down and continue doing a bagging regressor, okay? So here, I'm going to do a regression using the trained diabetes data set. And what? I'm missing the mean square error, which is a metric. I must have it somewhere here. Have to go back. Okay, this one, okay. So I'm using okay, so I can continue. I was missing the library for the root mean square. Was it? Too many rows. I should split this um, large Jupyter notebook into 2. Okay, next time. So, okay, so now I have defined root mean square. So this is the root mean square error for the regression on the diabetes data set, and see that what is the mean square error between the prediction and uh, and the real data. So that's using a bagging regressor. Remember, we are just using different data sets and different base models to create the result. And then we can do bagging classifiers using naive Bayes, which is another algorithm. So naive Bayes I'm going to import Gaussian naive Bayes from scikit naive Bayes, and I'm going to use a bagging classifier, 20 estimators, and the base estimator is a Gaussian naive Bayes. And what's my error now? Base estimator. Okay, so what? I'm jumping. Sorry. Let me do this. Yeah, sorry. I'm going to execute everything. And so it's a sequence. Okay. And then I'll explain. So it's running everything. Got it. Got it. Feature engineering. That's the relevance of each variable. We do the strength split for the penguins. We use decision trees for the penguins. We evaluate the precision classifier for the tree classifier. We compute the accuracy. We create the columns for the penguins, and we visualize the tree. Remember, we prune the tree. We play with the different alphas, and the different alphas, we select the alpha that give us the best accuracy. So we can prune some rows from the tree, and then we can compute how many nodes and what is the alpha value, and how many, what's the depth of the tree. We already saw that, and that's the accuracy, the decision tree regression for the diabetes data set. Everything is running. The accuracy for the decision tree model, comparing the train root mean square error and the test root mean square error, and then we can find the possible alpha that gives the best results. We can continue. We can plot the different trees, and then we get into ensemble learning. We already see this, the bagging regressor. We already saw, oh, this is an error. Explain error, okay. Good thing about the Google Colab is that it can suggest how to, okay. So let me place this, copy, and to replace this. Mhm. Okay, now what? Copy everything. Copy everything. And I'm going to add code. And okay, so this is Google Colab suggestion. I don't see, oh, instead of base estimator is estimator. Okay. Shift enter. And then continue. Yes. Yeah, so this cell was, I had to replace, instead of a base estimator, the an estimator, and everything will work fine. So now I have the Gaussian naive Bayes and prediction. and training and print the accuracy. So I have a 86% accuracy and 80% accuracy between the first one for the testing and the second one for the training. And then I could do a voting classifier. So going to import everything. The voting classifier from, and then the linear model logistic regression, the Gaussian naives from the naive base, and the random forest classifier. I have three classifiers, CLF1, CLF2, CLF3. The first one is logistic regression, the second one is random forest, and the third one is Gaussian. And then I'll have the estimator using voting classifier. So what I'll do is I have three algorithms or three base models for the logistic regression, random forest, and Gaussian. And then I'm going to do voting classifiers using the three models, but with different voting. Voting hard, voting soft, and voting soft with different weights. Let me close this part. In different weights. And so I'm going to do the voting classifier in three ways. And then I'll see what is the result for the first voting classifier. And I'm doing for the second ensemble and for the third one. And then this is the accuracy with for the first ensemble classifier. The accuracy is 0.98, 0.99. For using a hard vote, so for example, the logistic regression sees a 98% accuracy, random forest is 1, Gaussian naive is 0.86, voting classifier will be the combination of, so it's going to take the average of the value, so it's 98. Using the second ensemble, using the three classifiers, and so you have different results. The logistic regression again gives 98. The random classifier is 1, random forest is 1. Gaussian naive is 86, and voting classifier is 98. So that's a soft vote. And the third one is adding different weights. So again, you have the individual results, and then the voting classifier will have using different weights for the model. The weights is the second base model has double weight than the other models. So that's the result. Okay. And finally, the random forest classifier. Again, we're going to import random forest classifier. We're going to use the training data for using the penguins data set. And we're going to use the random forest model to predict once you have trained, and then measure the accuracy. The accuracy is 1. And this is another way. Okay. All right. I'm going to go as well as you're doing classifier using random forest, you can do regressors using random forest. So we import the random regressor. Our model is random regressor, and we fit using the diabetes data set, and then we predict, and we measure the mean square error, it's 55, and we do the same thing with the prediction in the training model. So the error is 21, and we have a score here. All right. Similarly, we can use AdaBoost, and it's about the same. Or you can use gradient boost. And we have XGBoost classifiers. So you have an example of all the different algorithms for doing classification or regression and doing the ensemble learning. Okay. So you have this example, and then you can run it, you can adapt it, If you're doing a classification problem or you're trying to do a regression problem, then you just adapt your data set. Remember to start your data set and then make the split training and testing, and then fit your model, and then do a prediction, and then apply all the metrics. Okay. All right. Any questions so far? It's a lot, but you have an example to work. Okay. All right. Any questions for me, Brandon?
Yeah, I was thinking, I mean, you have in this, it's a big collab doc and it's got all these different types. In your like normal workflow, like if you're doing like a prediction type thing, would you normally like would you do it differently? Where would you start with? I'm kind of wondering like how different it would be um starting from scratch on a project.
Well, first you have to have a clean data set.
Yeah.
And then once you have your clean data set, are you in your data set, are you trying to predict a class or you're trying to do a regression? So those are two different problems, right?
Yeah, so I got a classification problem.
So a classification, in the case we're using the penguins and we're trying to classify, I don't remember if we were classifying the gender or we were classifying the species, but you train you start with your data set, you have your 3 species of penguins, and then you select a part for training your model, and then you're trying to predict the label or the species of a penguin. If you know the weight, the flipper length, the culmen depth, the culmen length, and body mass, then can you predict what is the species, right? So
Yeah.
that's a classification problem. In a regression problem, let's say you're trying to predict the weight of a penguin, or you're trying to predict the glucose from the diabetes data set, right? So from all the different physical variables from a person that includes the BMI and weight and pressure, can you predict if the person has diabetes or what is his glucose or her glucose level? So that's a regression problem. You're trying to predict a number. And in a classification, you're trying to predict a label.
Mhm.
So those are basically the only two top types of problems you can solve in classical machine learning.
Yeah.
And what we have been seeing today is that every model in machine learning sees the data set differently, meaning that if you have a data set with 10 variables, let's say you have the data set for the penguins, and then every model will have different weights for the for the for the for the body mass. They will have different weights for the flipper length, the culmen length, and culmen depth. So every model will see different. When you do ensemble learning, you combine different models in order to improve your accuracy or to you decrease your bias, right?
Yeah.
So that's the advantage. You're using several models in order to increase your which is basically you never do a machine learning model using just a single model. You always be doing ensemble learning, combining different models in order to improve your accuracy.
Yeah.
Because of the fact that every model sees the data set in a different way. Every model see different ways of relevance for the variables. And this is a way of eliminating or diminishing all these differences. So that's the relevance of the ensemble learning. Okay,
Nice.
save. Okay, any other questions?
No, I think I'll have to come back to these collabs when I'm getting a chance to actually practice with the methods.
Okay. All right. Let's see. Okay. So stop sharing. And so next week the talk is about reinforcement learning. So let's see. So that's the talk for the next session, reinforcement learning. You have the notes in notebook. Okay, so that's what I have for today. And if there's no more questions, thank you.
Thank you.
Right. See you next time.
See you next time.